start recording, right? So I'm going to stop the video just to make sure that you get right. And I hope all of you can see my shared screen, which is about black holes. And so if I summarize what we have done last time when we met, remember we had a separate PowerPoint presentation that I did with you about the fate of these the end state of these high mass stars after the supernova explosions, right? So this is about type 2 supernova. And by the way, this reminds me that there is a nova that was visible. Right, so can one of you confirm me whether you can hear me clearly? So I guess the connection went down for a minute. Can you hear me? Hello.
Yes, sir, we can hear you now.
Okay, thank you. Right, so let me share the screen. Right. So what I was telling is that so we have discussed about this final stage of stars after this type 2 supernova explosions, and this is specifically about high mass stars. And I told you that what would happen is this remaining core of the star after the type 2 supernova explosion will become a neutron star, and if it is if it exceed a certain mass, then it will become a black hole, right? And so that was about the stellar mass black holes. And under the black holes, then we talked about different types of black holes and different properties of black holes, and some of the evidences to tell that we have detected black holes. And under that detection of the gravitational waves are one of the major findings to tell that there are black holes now. I mean, as one of the strongest proof for the black holes. So that was one of the first direct evidence that we have about observation of black holes. And then I moved into this section that you can see here, which is about the mathematical background about black holes. And we specifically talked about the Schwarzschild radius here, which I have also talked earlier in the previous chapter. And then, so what we are going to discuss here is, we are going to use, I discussed about these main properties about the for a black hole, that is mass, angular momentum, and electric charge. And based on the properties you have for a black holes, we are actually using different type of metric to describe these black holes, right? For example, the Schwarzschild metric, which we have discussed in the earlier chapter, will be used to describe black holes with mass only. So the only property that they have is only the mass. And if we have all these other, right, so I guess the connection went off again, and I think I have reconnected here again. So let me know if you cannot hear me, and let me share the screen again. So it seems that the connection is weak today. Right. So what I was explaining is that we can use different type of different metric for these different properties of black holes. And what we are using here is, and there was a section about the classification of black holes by size, which I have discussed last Saturday, I guess. and we were right here after that. And what I want to explain here is when an object is falling into a Schwarzschild black hole, what would happen? So I have selected only to talk about the Schwarzschild black holes because if we consider different properties of these black holes, then you have to go for different metrics, right? So which will make things a lot complicated than this simple type. So we will only talk about Schwarzschild black holes, which can be explained using the Schwarzschild metric. Now, so the Schwarzschild black holes are the black holes that you only consider the mass of the black hole, and so we can explain those Schwarzschild black holes using the Schwarzschild metric, as I have mentioned here. And so what we are going to discuss is how it feels when we consider about falling into a Schwarzschild black hole. So what are the things that could happen, right? So what we will look at this in two scenarios. So we will look at the time it takes for an observer to reach the event horizon and then travel towards the central singularity, right? So you can, so remember that I told you there is a region, or there is a surface, a hypothetical surface that you define as the event horizon, where if you cross that event horizon, you can't come back, right? So that is the idea. So we are going to discuss the time it will take for an observer to reach for that event horizon and then travel towards the central singularity, right? So remember that I talked what central singularity means in previous chapter. And so we are going to look at this scenario using two observers and two perspectives. That is a freely falling observer himself using his own clock. So that is, for example, think yourself that you are going towards a black hole and you have a clock with you, right? Now you are freely falling towards a black hole and you are going to, so we are going to discuss how the time works. So how long will it take for you to go towards the event horizon and from the event horizon towards the central region of the black hole, and then for a stationary observer. So let's say, so you and let's say two of you, and one decided to go for a black hole, and you uh, make a rocket or something like that you could use, that you can go into the black hole, and then you are going to fall into the free fall into the black hole in this space, and one of your friend is looking at you from Earth, right? So that is the stationary observer watching the fall and measuring from his own clock. So he has his own clock and he is going to measure how long will it take for you to cross the event horizon and fall into this central singularity, right? So these are the two scenarios. Now let's look at one by one and see how can you, I mean, what will happen in these two scenarios when it get close to black hole, right? I mean, you already know that the distance observer sees the fall taking an infinite time. Falling observer records a finite time. I mean, this is I already told you, right? Actually, what you will see is this distance observer, the friend who is looking at you from here, will see that it will take an infinite time to cross the event horizon. So basically what that means is you will never see that your friend crossing the event horizon. Right? However, your friend who is freely fall into the black hole will record the finite time. So he will cross the event horizon and will fall into the central singularity of the black hole within the finite time. So those are the two scenarios. Now, what I am going to show you here is from the knowledge that we acquired from the previous chapter about the Schwarzschild metric, how we can mathematically prove this, right? Which is interesting. Now, for that, let's consider the first scenario. So that is how this moving observer observe the time. And let's consider the motion of a radially free falling observer, right? So let's say you are falling into the black hole and you are the observer now. Now this implies that the object is moving straight down towards to the center of the black hole. So think about this scenario is that, so you are free falling into the black hole and you are moving straight down towards the black hole. Now what that means is that your phi coordinate should be a constant, right? So you are only traveling or moving in the radial direction towards the center of the black hole. So which means that your phi coordinate should be a constant. So you are not changing your phi coordinate because that is the angular coordinate, right? And because of that, if you remember this equation that we derived using the Schwarzschild metric. So let me go back to this earlier chapter about the Schwarzschild metric. It has equation 37 right here, and this note is already available for you. So that is this equation, right? Now I'm not going to go into details, and we have proved all these equations in the last chapter under the when we talked about the Schwarzschild metric. Now what we are using here is the Schwarzschild metric, right? And because of that, hopefully you remember this equation 37. So if you can't remember, just refer to the equation number and go back and check the note, right? And right. So this is the equation that I'm going to use here. Now let me go back to this one right here. So that is this equation 37. And it says J over M equal L, which is equal to R squared d phi over d tau. Now what I want to tell here is that when phi is the constant coordinate, d phi over d tau should be equal to 0, right? Because phi is a constant. Now if you are falling towards the black hole in the radial direction, so that means if this is 0, then your J value should be equal to 0, right? And now if J is equal to 0, there is another equation called the radial motion equation. And let me put these equations, right? The radial motion equation, which is equation 36 in this previous chapter, and I have written it here as well as the equation number 2. And this is also something that we proved in the previous chapter, right? So it is the same equation. And if you go back and look at equation number 36, it is this equation. And if J equals 0 in this equation, this term J will be equal to 0. And what would happen is this whole term will be equal to 0 and it will go away. And you can rewrite this equation 2 here by making J equal to 0 in this way. So that's what I have shown here from equation number 3, right? And after that, if we assume that this freely falling observer start at rest from infinity, right? So if it start at rest from infinity, that is when R goes to infinity. So let me just make it instead of equal, let me have an arrow here, which makes more sense in mathematics, right? So if we assume that this freely falling observers start at rest from infinity, so that is a distance that is so far away, we can assume that the energy can be written as m E equal mc squared, right? So that's the general expression for E if you are at rest, right? So I guess all of you know about that. So which means you can plug that value of E right here into the equation, E equal mc squared. So once you plug it, you can clearly see that this right hand side of the equation will become 0, right? So all you I will have is this term right here, dr over d tau, and this term right here, 2gm over c squared r, right? And then you have this equation by having r goes to infinity, and this will give you, right? So there's here is a square that shouldn't be here. We have it and rename the functions, right? So the dr over d tau will be square root of plus or minus square root of 2gm over r. So that is the final equation that you get. And now you have positive and negative square roots here, and we are going to select negative square root here by considering the fact that r is decreasing for freely falling object, right? Because when you fall towards the black hole, the r, which is the radial distance, is decreasing, right? Now considering that, we are going to take the negative square root of this equation, which is equation number 5, and then we are going to integrate this equation between two arbitrary points r1 and r2, where r2 less than the r1, right? So that's in this way, and you can see that I have taken only the r to the left hand side, which will give you r to the power half, and I guess all of you can integrate this expression, right? And 2gm, square root of 2gm and t tau, so that is the proper time between r1 and r2. And once you integrate this, so I have given here this as an exercise for you, because it is a simple integration, so that you can do this integration yourself and find the answer. And once you do the integration, you will get this equation for the proper time between these 2 points r1 and r2, right? So that is tau equal 2 over 3c square root of rs times r1, the power of 3 over 2, and then r2 is the same power, right? Minus r2. So make sure that you try this based on this equation, right? So basically the problem is basically to solve the integration. So that's all. And if you plot this expression with the proper time and the r coordinate, this is the graph that you would get, right? So this is, I have named it as the falling into a black hole, proper time tau and the radial coordinate r. So that this is the relation between the proper time tau and the radial coordinate r. And according to the above equation, freely falling observer measures the finite time to both pass through the event horizon at r equal rs and travel towards the singularity at r equals 0. What that means is, if you look at this graph, and also you can directly tell it from this equation as well, when tau, when you have this the Schwarzschild radius, which is sorry, at the event horizon, that is when r equal to rs, rs is the Schwarzschild radius, you will still have a finite value for the time, right? So the expression will give you a finite value. And also when you go into the singularity, still you will have a finite value. The singularity means here when you consider about the r1 and r2, r2 is less than 0, so the r2 will go into 0, right? And still you will have a finite value there, right, for the proper time. So which means for the observer who is measuring the time, that is the free falling observer, when he measures the time, he will not have any issue, and what he will have is a finite time to cross the event horizon, and also a finite time to fall into the singularity, right? So this is what this equation means, right? Now I expect that using this kind of equation, you should be able to derive these simple expressions, right? For example, the facts that when r goes to infinity, it should be equal to mc squared, and these kind of things, I expect that you can logically think and apply here, even in an exam. And then I have a problem here for you. An observer starts to free fall from infinity towards a 3 solar mass black hole of radius rs, which is equal to 8.85 kilometers. How long does it take the observer to fall from R1 equal 30 kilometers to the event horizon, right? And shall we try this first question? I will leave the other two for you to do at home. So let me get the equation to the screen. Now, so I will give you, let me say 5 minutes for you. So plug these values and show that, give me the time that it will take for this observer to fall from R1 equal 30 kilometers to the event horizon. Now, for this case, I have given you the event horizon. And remember that you can even can find the event horizon from the equation that we have previously defined, right? The event horizon, the Schwarzschild radius, right? The Schwarzschild radius is the distance to the event horizon. And can you try this one and give me the answer? So I will give you, let's say, 5 minutes. Just fall from R1 equal 30 kilometers to the event horizon. I just need to make sure that you understand these concepts and so that we can discuss it after that. If any of you have a question like how to start or something like that, then please feel free to ask, right? We just need to, use the equation and plug the values to get the answer. So that's it. Right, so I have one answer. How about the others? So I will wait for a few minutes. So I would like everyone that you do it yourself and have the answer here so that I can get an idea that you are following what I am doing here. Who else would like to answer? So I got two answers, one from Amila and the other one from Kesha, right? How about the others? Right, so I guess it's time is over now. So please try yourself and or let me know if you can't understand how to do that, right? So let me just show you how to use the equation and proceed with this. But I assume that all of you can do this yourself. Let me share a different screen right here. Right. Right, so I hope you can see my screen. Right, I got another one. Time. I guess Amila, you probably need to check your calculation, but let me show you how to do the substitution. I guess all of you know about it. The equation that we have is 2 over 3 times C and square root of R is and R1 to the power 3 over 2 minus R2 over 3 over 2. And actually we are given the values of R1 and R2. R1, so this is something that you need to understand. R1 should be 30 kilometers because that is the larger value. And R2 is the value of the Schwarzschild radius. So that should be RS, which is equal to R2 as well. And that is 8.85 kilometers, right? So this is all that you need to know. And then once you substitute values, so what you have to do is 2 over 3 times, and the velocity of light, everybody knows the value. That is 10 to the power 8 meters per second. And then the square root of Schwarzschild radius, that is 8.85 kilometers. To change it to meters, we have to multiply it by 10 to the power 3. Now, this may be a point that some of you may get it wrong. So make sure that you use these correct units when you substitute it, right? Even in exams. And then you have to again change it to meters, R1. So that is 3 over 2 and then 8.85 times 10 to the power 3. And this is also 3 over 2. And when you do all these calculations, your answer should be 1.03 times 10 to the power minus 4. Or you may get 1 or 2 decimal places different, but that is okay. I think the Kesha got the same answer, so it should be the correct answer then. Excuse me. And this is 0.103 milliseconds, right? So this should be the answer that you get at the end. And this is the time it takes for the observer to fall from R1 equal 30 kilometers up to the Schwarzschild radius, right? And if you do the calculations, you will find that, and the graph also tells the story from the Schwarzschild radius. If you try to find the time it takes to fall from the Schwarzschild radius from the event, that is from the event horizon to the singular, it will be very small value like 0.02 milliseconds or something like that. So just work on the problem in the similar way. So let me share the note with you. So I assume that you can see the note again, and if you can't see it, let me know. Now for all others, please try the problems yourself and do the calculations yourself, right? It is just a substitution that you have to do. Now that is, you can see that all of at each and every time you measure a finite time, right? Now let's look at when you are observing this falling observer from here, right? So assume that, so that is the next scenario. Assume that an observer carefully looks at an object falling into a black hole. So that is you watching that something is falling into a black hole, or this is pretty much similar to a star undergoing a total collapse, right? And so let's find the journey time for light signal emitted by an object freely falling into a black hole and received by a distance observer. Let's take, because when you see an event, that means you should receive a light signal from that event, right? So that's what normally happens. Now at this scenario also, we will assume that both object and the observer are in the same radial line. So which means your coordinates, that is d theta and d phi, we assume both are equal to 0 and you consider only the radial direction. Now, for the light signal path, you can directly write that ds equal to 0, right? So that is called null geodesic. And I mean, in special relativity, you probably have this light like time like intervals, those kind of things, right? So because of that, I assume that you can understand this. For a light signal, this ds squared, which is equal to c squared d tau squared, should be equal to 0. And this ds is defined in the previous chapter. That is defined from this equation. And if you go and look at the equation number 2 in the previous chapter when you define the Schwarzschild metric, that is this equation right here. At the very beginning, we have defined this equation ds squared, right? And that is actually the metric that we defined. And for the light signal, this ds squared should be equal to 0. So that's what we are going to use here. And if ds squared is equal to 0, then we know that we assume only the radial direction. So which means this d theta and d phi will be equal to 0 as well, which will give you the left hand side will be equal to 0. And for the right hand side, you will have only these two terms because d theta and d phi both will be equal to 0, right? And if you simplify the equation in that way, you will have only these two terms that will be equal to 0. From that, by manipulating these terms little bit, you can get an expression for dr over dt, which will be equal to plus or minus 1 c times 1 minus 2m over r. And also you can rearrange this to get dt over dr, which is plus or minus 1 over c times 1 minus 2 over 2m over r. And from here you can use the relation of the Schwarzschild radius, which is rs equal to 2gm over c squared, which is we have defined that is equal to 2m. And remember, what I am using here is all the terms that I defined earlier here, right? Remember, r is equal to gm over c squared. And that's how you define simple m based on gm over c squared, which I have mentioned here. So you have to follow these notes from the beginning to understand it, right? Right. So at the end, you get an expression for dt over dr. And then by integrating this, finally, after the integration, you will get this expression t2 minus t1. Now the t2 is not the proper time. This is the time measured by this distance observer, right? So that is what we are using here. And here you can actually derive few different things. One thing is that if you do not have a central mass or the central mass is negligible, so this is the normal condition that we have in our day-to-day life. So what that would mean is the Schwarzschild radius will be equal to 0, right? So that comes from this equation. If the central mass, this m, goes to 0, if it is negligible, rs will be equal to 0. Now, if you plug that rs value here in this equation, you can see that if rs equal to 0, this whole term will be equal to 0. What you will have is the time will be equal to distance over the velocity of light. I mean, this is for light signal, right? So that's the usual equation that we get in the flat space. But what we want to look at is what happens when this falling object approaches to the event horizon, right? So that is when r goes to rs. the Schwarzschild radius. So then what will happen is this R will, yes, when R goes to RS, what will happen is this expression right here, T2 minus T1 will go to infinity, right? So just check here by having R1, when it goes to RS, you can easily see that this expression will go into infinity, right? And what will happen, what that means is the photon journey time approaches to infinity. So which means this light signal that emit from this object, the time it will take to reach you will be infinite time, right? Now this is why you will never see that your friend who is falling into the black hole will cross the event horizon, right? So I hope you can understand it now. So that's why the distance observer would never see the object reach to the event horizon, right? So he will see that object like seems to be slowing down continuously, but he will never see that the object reach to the event horizon, right? And this is what I want to tell you at the end. So we have basically discussed the two scenarios, how it is measured by the freely falling observer and how it is measured by a distant observer. Now the freely falling observer wouldn't have any issues. He will measure finite times. However, when you are measuring, or when an observer, a distance observer measured this, he will never see that this object or the person across the event horizon, right? So those are the two scenarios, and there is another scenario that we have discussed in the presentation in last week, and also we discussed this in the previous chapter. So that is about the gravitational redshift when it gets close to the event, the black hole, right? Now what you can, so I have a problem here for you. Starting from gravitational redshift equation, show that the emitted wavelength of an object that approach to the event horizon is infinitely redshift as seen by a distant observer, right? And I assume that you can easily prove this. To start this, you can actually start this from the gravitational redshift equation that we have derived earlier. So let me show that equation for you here at the end. This one. Yes, right here. Here is the gravitational redshift that we have talked, and this is the gravitational redshift equation. So you can start from here and think about how you can prove it. And this is not that much hard to prove, and it is straightforward. So that's why I am going to assign that for you. You just need to use the equation V equal F lambda. So I'm just giving you some hints to try this. And in this case, for the light, it will be C equal F lambda, that because the velocity of light will be denoted as C. And all you need to do is, for these frequencies, you can actually substitute value C equal F to the two sides, and that will give you an expression that will come in terms of wavelengths, right? So the same expression you can write in terms of wavelength, emitted wavelength, and the observed wavelength, which once you have that expression, the expression will come in terms of, actually you can substitute here the value of the Schwarzschild radius if you want. So once you substitute it, and take an expression in terms of the Schwarzschild radius here, then you can check when R goes to the Schwarzschild radius, what would happen to the wavelength, and you will clearly see that it is infinitely redshifted, right? So that is what you have to prove here for this particular problem, right? So these are just simple problems. I just need to make sure that you can apply what you have learned here, right? So just go back to the previous chapter and look at the equation that we have derived for the gravitational redshift and try to apply here to see that mathematically you can prove this the emitted wavelength from an object that approached the event horizon of a black hole is infinitely redshifted, right? So this is as seen by a distance observer from the Earth, right? So this will convince you that the things that we have discussed about the black holes are that you can prove mathematically, right? And they are correct, right? So that is the last problem that you have here, and I will leave that to you. And once again, I am going to combine all these problems for you into a tutorial, maybe with adding some of the other problems as well. However, you have the notes now, so make sure that you can actually prepare your, do the problems and keep that with you, and you can submit everything at the same time. So once I post it as a tutorial, right? So I just want to give the problems a little bit ahead of time for you so that you can try those yourself, and you can get the help of the book as well if needed. Right now, this will finish the section that I want to talk about black holes, and this note is already uploaded. But either way, by the way, I will, once I do some corrections, like small corrections like this, I will re-upload the notes later. But you have the basic note that you can go through, which doesn't change the content. However, maybe if there are typing mistakes or something like that, then I will make those changes. Right now, anybody have any questions up to here? I am going to share the presentation right now with you, and we'll very briefly go through some of the information which is available there. That is because I want to have some basic knowledge about this active galactic nuclear section when I talk about the cosmology. So let me share this screen and just I will scan through this presentation. I am not going to go through each and every slide. And so active galaxies are a little bit different than the galaxies that we have talked before. And if you remember that we have a system called Hubble classification previously to classify galaxies into, ellipticals and spirals, and then, barred spirals, unbarred spirals, for different types. But astronomers have also discovered a different set of galaxies, which is a small fraction, which are very unusual, right? And these unusual galaxies are called active galaxies. The features that they have is that these galaxies have a nuclei, which is at the central region. And this nuclei is, every galaxy have a central region, right? But these nuclei that they have in these active galaxies are much brighter compared to the normal galaxies. And in addition to that, they also exhibit some unusual properties, particularly in the non-visible part of the spectrum, right? And there are mainly three types of active galaxies that we talk. So those are called C-FET galaxies, radio galaxies, and quasars. And then I have some information about the C-FET galaxies, what are the main features of those, and then some of the information about the emission lines of these Seyfert galaxies. And then there is a section about talking about what powers Seyfert galaxies. And then the second type of active galaxies, those are the radio galaxies. So that's, as the name suggests, they emit a lot of radio waves. So that's why you have the name called radio galaxies. And here are some images of those. And the third type is called quasars. And this is the area that I specifically that I want you to pay some attention. In 1960, astronomers discovered a new class of object in the sky, and these objects looks like very faint blue stars. However, they were also strong radio sources. So they have discovered this in 1960s. Because if you look at the normal stars like our sun, they are very weak in radio signal. They don't emit that much radio waves. Therefore, even though these particular stars looks like faint blue stars, due to the fact that they emit strong radio sources, these objects were real puzzle at that time. And then after examining the spectra of these objects, this astronomer called Martin Schmidt showed that they were way beyond the Milky Way itself. So which means these particular objects are so far away from us. So what that means is they are largely redshifted, and this implied they should be extremely luminous, right? And they should be also not stars, because you cannot see individual stars from that far away, right? So that doesn't make sense. So these, even though they looks like stars, they should be some different kind of objects. If they are, because they are so far away, they are largely redshifted. And now we know that these objects are normally identified as quasars, right? And these quasars are normally reside in the centers of galaxies. So that's why it is one of these active galactic active. That's why they have become one of the types of active galaxies. And so what we know now is that these active galaxies, all type of active galaxies and also the quasars, they are fueled by accretion of gas onto a supermassive black hole. We know that all these galaxies have a supermassive black hole, but not all galaxies you can see these quasars. Because our own Milky Way, we don't see something like that. So to make these active galaxies, there must be a large supply of gas being accreted onto the black hole, right? So the black hole, so there should be a large supply of gas that should be supplied to these central supermassive black holes to make this nucleus active in these galaxies, right? Now this doesn't happen for all the galaxies. We know that almost all the galaxies have a supermassive black hole, but not all of them have this active, not all of them are like active galaxies like this. To become active galaxies, even though you have a supermassive black hole, so there should be a large supply of gas that is being accreted towards the black hole, right? Now, this happens in one way, that is from galaxy interactions and mergers, which probably we have talked earlier. And so if you have these mergers between galaxies and some galaxy interactions, then there can be inflow of gas onto the central black hole, right? And this is also supported by the fact that these active galaxies and especially quasars were more common in the past than they are now. These quasars are very common when you look at high redshift universe, that is the very early stage of the universe. So that means the idea is that at that time you had a lot of mergers and interactions between galaxies than what we see now, right? So that those mergers and interactions should have helped to create these active galaxies at that time by creating a lot of matter towards this central supermassive black hole, right? So that's the idea. And so I just need to give you an idea about, especially about these quasars here. So that's why I put it here. And I didn't omit the other information that I have here, because there may be somebody who is interested about knowing about these things, because these are separate research fields and those kind of things. But if any of you are interested, but what I want from you is that you should know that there is a type called active galaxies, apart from these normal galaxies that we have talked. And there are basically three types of active galaxies, and just have an idea what is the special thing about these active galaxies. That is because they have a very active nuclei. And other than that, the CFAT and radio galaxies, just get a basic idea. Other than that, it is important that you know about these quasars, which are very high redshifted objects, because those observations of quasars are somewhat related to the cosmological aspects. That is, we talk about something called homogeneity and isotropy of our universe, and this observation of quasars came as an evidence for that. So that's why I want to talk about that little bit. So make sure that you go through this presentation and have a general idea about the active galaxies and quasars before we start the next section about this cosmology, right? Right, so I'm going to finish today's lecture from here. Now, anybody have any questions up to now?